In this example, we're going to be looking at the motion of a reciprocating saw that's shown here in the figure. The key components of this is a flywheel, which has a shaft passing through its center O, and this flywheel is rotating at a constant rate. There's a coupler, AB, which goes from the circumference of the flywheel over to the saw blade there at A, and the saw blade A is constrained to be moving along a horizontal line. So what we want to do is, with that known information, we want to end up with a number here for the acceleration for the saw blade and the angular acceleration of the coupler arm AB. What I've done is I've drawn a picture of the system when theta is 90 degrees. That's where we want to find our answers. I've drawn that picture there in the bottom right hand of the screen. I'm going to be using X and Y, a traditional X to the right and Y vertical. And again, the goal is to do an acceleration analysis, but by this point you've probably seen that in order to do that you need to do velocity first. So we will first look at velocity, and we're going to be looking at this link by link. We're going to look first at the drum. And the drum velocity equation, we're going to go from the center of rotation O out there to point B. So VB is equal to VO plus the omega for the flywheel, omega F, cross with a vector which extends from O to B. Since O is the shaft, the rotation shaft of the flywheel, velocity of O is a 0. Omega F is going to be theta dot. We're given a number for that. It's rotating in the counterclockwise sense, so theta dot K makes sense. And then the vector which goes from O to B, that's going to be a minus Ri. So from this we see that K cross I is a J, so this is a minus R theta dot J. So that's for the drum. Now for coupler AB, we're going to write down the same kind of equation and say that velocity of B is equal to velocity of the other end, A, plus the angular velocity of the coupler AB crossed with the vector which goes from A to B. Before I write this down, what I'm going to do is look at the details here of the trig. I've got an angle here, phi. And from phi, the angle phi, we can see that if this coupler length is L, then sine phi is equal to this known distance there of D divided by the length of the coupler L. So from that we can get a numerical value for phi. A is constrained to be moving along the x-axis. Okay, so I'm just going to write that as VAI. VA is an unknown. Omega AB, that is an unknown, so I'm just going to write that omega BK. I'm going to write as plus and then let the math tell me whether that's a good guess or not. Then the vector going from A to B is going to be an L cosine phi I plus an L sine phi in the J. So when I do my omega cross R and add it to VA, I get VA. K cross J is a minus I, so this is a minus L omega AB times sine phi. The J component, that's going to be L omega AB cosine of phi. And of course that's in the J. So what I've done is written down a velocity equation for the flywheel. I've written down a velocity equation for coupler AB, both in terms of the velocity of NB. two expressions for the same thing. So if I equate these, I know that the I components of one have to be balancing out with the I components of the other. So the first equation, there is no I component, so that's a 0 on the left side. And then I have a VA minus L omega AB sine phi. And the J component equation says that on the left-hand side I have a minus R theta dot. On the right side I have an L omega AB times cosine of phi. The first equation we really don't need, but the second one gives us what we do need. We find the angular speed of coupler AB is going to be equal to minus R theta dot divided by L cosine phi. And we have all the numbers that we need. We're given the rotation rate theta dot for the flywheel. We're given R, we're given L, and we just found phi. So whatever number that we get, it's going to be a negative sign there in front. The negative sign simply means that I originally assumed plus, originally assumed counterclockwise. I was wrong. The negative sign means that, so therefore it's in the clockwise sense. So that gives me omega AB, a number. Now what I'm going to do is do the acceleration analysis. Repeat the same process as for velocity. For the drum, I'm going to say that the acceleration of point B is equal to the acceleration of O plus alpha for the flywheel crossed with the R vector, which goes from O to B, minus omega flywheel squared R O to B. O is the rotation shaft for the flywheel. That's a 0. It's given that theta dot is a constant, so alpha is a 0. So we have a minus theta dot squared. The vector going from O to B is a minus Ri. So the acceleration of B is a plus R theta dot squared I. Now we look at coupler AB. We say the acceleration of B, in B, I can write that in terms of the acceleration of the other end, A, alpha AB, crossed with the vector which goes from A to B, minus omega AB squared, RB with respect to A. Okay, so A sub A, we don't know what that is, but we do know that it's only in the X. So this is A sub AI. Alpha AB, don't know what that is. Don't know which way, what sign it has or the magnitude, but I do know it's about K, so that's an unknown. The vector which goes from A to B is going to be an L cosine phi in the I, L sine phi in the J. Same thing here, I get omega AB, which we've already found, that's squared, times L cosine phi I plus L sine phi in the J. So I cross through my alpha and R, I group together my terms. The I components are going to be A sub A. K cross J we know is a minus I, so this is a minus L alpha AB sine phi minus L omega AB squared cosine phi. That's in the I. The J components are going to be L alpha AB cosine phi and a minus L omega AB squared times sine phi. So just as before, when we were looking at velocity, and when we did the velocities, we had two expressions for velocity b. Here we have two expressions for the acceleration of b. They have to be the same. So if I equate these, balance out my coefficients, I'm going to have an equation for I and an equation for j. So let me jump to the j equation. Let's see what I can do with that one. The first equation, there is no j component, so there's a 0. The right hand side, there's an L alpha AB cosine phi minus L omega AB squared sine phi. In this case, the L's cancel out, and what I get is alpha AB, therefore is equal to omega AB squared times sine over cosine, which is a tangent. And since this is a plus, this tells me that my original assumption up here that it was plus was correct. So my assumption being a plus would be counterclockwise, so that's what I get. So I have alpha AB. What we're asked to find here is alpha AB as well as the acceleration of the saw blade A. So I need to come and use actually now the I components. For the first equation, it's r theta dot squared. The right hand side, I have an A sub A minus L alpha AB sine phi minus L omega AB squared cosine phi. So from this equation, I see that the acceleration of the saw blade A, that's equal to r theta dot squared plus L alpha AB sine phi plus L omega AB squared times cosine phi. So we saw above that alpha was a plus. So this is a plus. This obviously is positive as well as that. So A sub A is plus, which means that the acceleration of A is to the right. So in the end, what I write down then, therefore, my final answers are the angular acceleration of the coupler arm AB is that number that I found above in the k direction, and the acceleration of A is the number I just solved for A sub A in the I. So these are the answers. Let's go back to see what we did. In a mechanism like this, in this particular one, we really have two links. We have the flywheel and the coupler AB. So anticipate this. For every link that you have, when you do velocity analysis, you're going to write a rigid body kinematics equation for each link. So I did that. Velocity for the drum, velocity for link AB, was able to equate those two to solve for the omega for AB, which is what I had to have. Repeated that same process for every link. For each link, the drum and AB, I wrote an acceleration equation. I equated those, and that gave me the necessary equations to solve for the unknowns. It's a procedure you're going to need to get used to doing, because that's the way you need to do it. For every link in the mechanism for velocity, write a velocity equation. For every link in the mechanism for acceleration analysis, write an acceleration equation. and that will generally suffice in terms of the number of equations that you need to get the answers.